Okay, hello everyone. I'm Mehmet Fazil Kapci, and I'm doing my PhD right now in the Norwegian Science and Technology University. And the topic of the talk today for me is the effect of hydrogen on the micromechanical behavior of alpha titanium. So let me start with the outline. I would like to first introduce the titanium microstructure and also the hydrogen uptake into this titanium microstructure. And to understand the effect of the hydrogen on this titanium-based metals, we perform series of micropillar compression tests. And so in order to show that, first I will be showing the orientation and geometry of these micropillars. And then I will go with these in situ micropillar compression tests. And lastly, there will be molecular dynamic simulations in the same orientation for these tests. Okay, let me start with the introduction first. So the titanium has two crystalline structure. One of them is the alpha titanium, exists in the HCP crystal, as you can see in this figure. And there is also BCC beta titanium. And the phase rise formation usually takes place around 890 degrees Celsius degree. And depending on the alloying elements inside it, it can be in the alpha alloy form or beta or alpha plus beta alloy form as well. However, these titanium alloys are also susceptible to hydrogen embrittlement. And you can see in this figure, once the hydrogen diffuses into matrix, they can form hydrides, which has brittle structure. And they can be in the gamma hydride, delta, or epsilon hydride form, depending on the local concentration of the hydrogen. So, so far, there are studies investigating this embrittlement effect of hydrogen on the titanium-based material. For example, in the alpha plus beta alloys, the hydrogen can diffuse through this beta phase, which has much more high diffusivity compared to HCP case, and eventually the hydride can form in the phase boundaries. And due to the lattice expansion coming from this hydrogen diffusion, the nanocrest can occur and further go through the both in alpha and beta lattice as well. Also, these titanium hydrides can also be formed within the lattice or within the grains as well as lamellar form, which has again brittle structure and initiate fracture under the applied stress. However, we think that it's also important to understand the effect in both hydride case and the solid solution case as well. So thus we first look at the effect of hydrogen on the alpha titanium or the HCP crystalline structure. So before that, let me introduce some of the slip system or the slip system in the HCP titanium. So in total, there are 4 independent slip systems in the HCP titanium, including the basal prism prime needle slip, and also first and second order prime needle slips as well. And so in order to understand the effect, we choose this prism slip to be investigated because it is the most dominant slip mechanism in the HCP titanium. And after selecting this correct orientation, we need to identify the specific grain so that we can activate this correct prism slip during our test. So in order to do that, you can see here the SEM and the EBSD image of the high purity titanium. And then we first identified this clear orientation, which is 2 -1 -1 0. So if we start from the origin and go through one corner of this HCP unit cell, it is the orientation of the 2 -1 -1 and 0 as well. And so here you can see the orientation map as well in this figure. So after deciding this orientation and identifying the identification of the grain, we fabricated the micropillars by using the plasma flip. And there are several, these are some details about the milling parameters, which we start with the 15 nanoamp and decrease the current until the 30 picoamp. And then these are the dimensions of the pillars, where we have the diameter 2.4, around 2.4, and length around 6.5 micrometer, with an aspect ratios around 2.7. For the micropillar compression test, we applied in-situ test, and for this we have two different charging conditions. One of them is the 0.05 milliampere centimeter square, and the second one is the 5 milliampere centimeter square. So we choose these two charging conditions to introduce both solid solution to see the solid solution effect. And secondly, we wanted to form hydrides within those micropillars and to understand the effect of the hydride formation during the prismatic slip. And in both of these conditions, we charged the micropillars in 5 hours. And of course, prior to these tests, we also performed this indentation test in the air condition as well. And here you can see the illustration of our charging setup, where we have the sample in here and the micropillars in the surface of the sample, which is filled with the electrolyte. And both we have the reference counter and working electrolyte. It's connected to potentiometer in that configuration. So let me continue with the results we get from this micropillar compression test. So for all of the conditions, we applied the 10 nanometer per second displacement rate. And also for all the conditions, we applied 1000 nanometer total displacement. And here you can see the stress strain response of these two different tests. First, let me start with the air one. In air condition, the yield stress was higher compared to the solid solution case. And we can see a sudden drop on the plastic flow, and it continues until some strain, and then it starts, the plastic flow continues with the large strain bursts and the drops in the stress. However, after we introduced the solid solution of hydrogen with 0.05 milliamp per second, we saw the decrease in the yield stress. And compared to the air case, the flow stress were more continuous, and strain burst in that case it was a bit more frequent and limited compared to air case again. However, when we introduced the large or the higher charging conditions, which is in that case the 5 milliamp per centimeter square, where we believe we introduced the hydride within the microstructure, the yield stress increased, obviously, and then also we observed the hardening phase with the introduction of these hydrides. And although we have compressed this pillar as well until the 1000 nanometer, as in the other two cases, the stress drop after some point, which indicates a kind of little fracture happened until it reached the 1000 nanometer. And here you can see the SEM images of these three conditions. As expected, and that we have the slip systems activated, prismatic slip system activated within on the two -1, and 0 direction, which corresponds to prismatic slip in that case. And in the air case, you can see large slip traces. However, I'm not sure it's visible from here, but in the solid solution hydrogen cases, you can still see the large slip traces, but there is also small intense slip traces as well, which indicates it's more continuous and frequent strain bursts happened during the solid solution. However, when we charge with the 5 milliamp per centimeter square, the behavior was pretty different, where we have high yield stress, and instead of a lot of slip systems we see in the solid solution hydrogen and the air case, instead we just see one fractured slip, and then also some deformed layers or the secondary cracks in the upper side of these pillars. And further analyze these hydrogenated cases, we took the STM images as well, as you can see in these two figures. So first one, this is for the low hydrogen concentration. We can say this for the solid solution hydrogen concentration, where we can see the slip traces, and there are also dislocations around these slip traces. However, in the hydride case, at the upper side of the micropillar, we can see large or the intense strain fields because of the hardening and the higher yield stress and the hardening mechanism as well. So after we also performed some molecular dynamic simulations to better understand the behavior of this prismatic slip under the effect of hydrogen. So in that case, instead of titanium, due to availability of the interatomic potentials, we use zirconium and hydrogen. But the zirconium is highly similar to the titanium in terms of the both crystalline structure. It also has HCP crystals and also shows the same slip system as the titanium. So, and we again use the same crystallographic orientation where we have the 2, -1, -1, 0 direction in the Z. And also we have this simulation cell size where the diameter is 25 nanometer and the length is 60 nanometer. And we performed 2 different simulations, one with the hydrogen and one without the hydrogen as well. For the hydrogen case, we just randomly distributed the hydrogen atoms into the crystal, into the simulation cell with the 10% atomic ratio. And there are other calculation details where we have minimized the energy before the simulations and applied the temperature and the pressure equilibration before the loading. And eventually we load these 2 different simulation cells with the strain rate of 10 to the -3, 1/picosecond. So let me continue with the results. So similar to the experimental ones, we see the decrease in the hydrogen, decrease in the yield stress after we load the system with the hydrogen. And you can see in this figure that this is taking the images from the 10% strain for the hydrogen and pure case. And although it shows no slip traces, in the 10% strain, the hydrogenating case already started slipping by the prismatic slip system. And this is the end of the simulation. You can see larger slip traces can be seen in the hydrogen case as well. And so this was conducted to understand the effect of solid solution in more detail or even smaller scale. Addition to slip system, we also checked for how the dislocation evaluation occurs during these simulations. And we can measure the dislocation length, or we can say the total dislocation density throughout the simulations. And you can see here, it's for the hydrogen charge case, it's a bit higher compared to the air or the pure simulations. And we can see that both the H and screw dislocations are active during the loading as well. Okay, so which brings to us the conclusion that, so we show that the presence of the solid hydrogen can reduce the critical shear stress for the prismatic slip in HCP titanium. And also we saw that the dislocation emission was facilitated by the addition of the solid hydrogen and lead to softening. And also we saw more continuous plastic flow and frequent and also limited strain bursts in the solid solution hydrogen case, whereas the larger stress drops observed in the air case as well. And lastly, higher hydrogen concentrations, which we believe to introduce hydrides into the microstructure, lead to increased yielding and hardening effect after the yielding as well, which results in brittle failure. Thank you very much for the attention.